Here we go. We have a algorithm, Boruvka algorithm. So it is the oldest algorithm to find the MST. I hope you are already familiar with the MST concept, and you already know DSU. It works on DSU. So I discussed in the Kruskal algorithm. So be sure to check out that video first, then come out to this video. So let's first read the problem statement. We have minimum spanning tree. So it's a weighted, undirected, connected graph with V vertices, E edges. Our task is to find MST. Graph is given as a urgency list, and we need to find the minimum spanning tree. The first point is the edge. Second point is the weight in the input urgency list. So we have this graph. In this case, MST is this. So 4. In this case, the MST is 5. So let's directly solve it using the Boruvka algorithm. So Boruvka algorithm uses cheapest cheapest edge for every vertex. So cheapest edge. So let me build a list for this. So here we have given 0, 0 to 8. So let me build. So that is enough. So what's the cheapest edge from 0? So from 0 we have 1. So 0 to 1 with weight 8. So we have this. Then 0 to 7 with weight, uh, 0 to 1 with weight 4. Then 0 to 7 with weight 8. So this is greatest. So we will not include this. From 1, we have a weight here. So from 1 to 0 with weight 4. Then from 1 to 2, this is weight greater than already present. So this is also weight greater. So let me change the color. Mm, so from 2 to 1. So first we store this 2 to 1. This is not good. So from 2 to 1 with weight 8. Then from 2 to 3 with weight 7. So this is smaller. Then from 2 to 8, this is more smaller. So we will include this. 2 to 5. So this is greater. So we will not include this. It's time for 3. 3 weight 3 minimum edge is 3 to 2 with weight 7. Then from 4 to 3 itself, 4 to 3 with weight 9. Then what do we have? We have 5. So from 5 to 6, we got 5 to 6 with weight 2. From 6 to 7 with weight 1. Then from 7 to 6, this is smallest. Then from 8 to 2 with weight 2. So before that, initially we fill it with -1 and maximum. Because why we are filling maximum weight? Because so we can compare. So first we fill this, then if this is smaller, we will add this. In this case, first we fill this, then if this is smaller, we will update it. If this is smaller, we will update it. If this is smaller, we will update it. So I have made a mistake here, I think. No, it is correct. So what we'll do? First, we will connect. We will connect it. So we have 0. So 0 as in edge from 0 to 1 with weight 4. So we will check, is 0 and 1 already connected? How do we check? We have DSU for this. 0, then 1, then 7, 2 here, then 8, then 6, 3, 5 and 4. Is 0, first we have this, is 0 and 1 already connected? No. So we will connect it with weight 4. Then we got this. Is 0 and 1 already connected? Yes. Is it 2 and 8 already connected? No. So we will connect this. So then we have 3 2. Is 3 2 already connected? No. So we will consider the weight. We are not literally building the MST. We are just considering the weight. We are only interested in the weight part. Then 4 and 3. 4 and 3 we will connect it with weight 9. Then 5 and 6. 5 and 6 where we have this 5 and 6 with weight 2. Then we have 6 and 7 with weight 1. Then we have 7 and 6, so it is already connected. Then we had 8 2, it is already connected. So we got three component. And initially what we have, so let me so first the initial number of components we have is vertices vertices, the number of different components. So different component initially we got is 9, because we have 9 vertices. Then we connected this, then we update our different component because we have joined a component. Then we have joined this, so we'll again update our component. So then we have joined this, we have again our updated our component. Then we have joined this, we have again updated our component. We joined this again, then we joined this, then we again. So what we got? After that we got three different components, but we want only one component that is connected to this. So we want one component only, but we got three. So we again have to do the same process. So we again reset our cheapest. So just reset your cheapest and fill just fill it with a value of minus 1 and plus infinity. Then 0, we have an edge here from 0 to 1. So we will check, is it is this is this means source and destination, is it already in the same component? Yes, it is already in the same component, so we will not consider this. So then we got 0 to 7, is it in the same component? No, it is not in the same component. So then we need to consider this, but let's first make a representative of this group. So I am uh, marking with 1. So let's make a representative of this. So let me use a different color. So representative of this group is 1, representative of this group is 2, and representative of this group, let's say 6. So then what we have to do, we again have to find, is this and this is in the same group? No, it is not in the same group. So we find parent of 0, parent of this value, is 1. So we have to store the value here. So the value here is minus 1 and plus infinity. And here value here I will have to store from 0 to 7. The distance is 8. Yes, that's it. Then from 0 to 1, it is already in the same group. From 0 to 2, it is in a different group. So I will store the answer in the parent of this group. So here 1, but the weight is same 8 and 8, so we don't have to update it. Then from 2, first value is this, so let me call it minus 1 and infinity. Then from 2 onwards, is it already in the same group? No, it is not already in the same group. So 2's representative is 2 himself. So then we'll update it with value. So 2 is connected to 1 with weight infinity. Then we go to this, is already in the same group? Yes. Then we have this, it is already in the same group. We have this, it is already in the same group. So side by side, let me also show you the code. So this will be the code. So it's just mess up. So I have to make a space. So here, so uh, we have this. Then inside this we have you and we. Then wait. Then we have to find the parent. Parent. So if we, after finding the parent, if it is already the same group, just continue. Then we need to get the cheapest. So this is the cheapest. We find the position. Dot get position. And if the value is greater, if the already present value is greater, so that's why we have stored infinity here. If the already present value is greater than the current weight, so just update it. And same applies for parent of 2. So we are not only updating parent 1, we are also updating parent second. So I think I have made a mistake. This is not infinity. From 2 to 1 we got 8. So this is 8, not infinity. So we have found 2's neighbor 1. Then let's uh, let's find out. Let's continue. We have 3. So 3 is connected to 2. 3 is also connected to 5. No, 3 is not connected to 5. So we have to consider this. But 3's parent is 2. I will store the answer in 3's parent. 3 weight is 14. 14 is already greater than 8. So I will not consider this. Then what's the parent of 5? 5 parent is 6. So we got minus 1 and infinity. But 5 parent is 6. Uh, so I have to store the answer here. So 5 is connected to 3 with weight 2. After that, we are done with 3. Let's find out for 4. 4 is already connected to 3. 4 is not connected to 5. So what is the 3's parent? 3's parent is 2. 3's parent is 2. And the is already value is already less than 10. So 4 and 5 we have to make a connection. So 5 parent is 6. The value stored is already less. So we are done with 4. Let's find out for 5. For for 5 uh, for 5 we have for 5 we have this 2. So 5 and 2 is not connected. So we have to make a we have to consider this. What is the 5 parent? 5 parent is 6. And we have to consider weight 4, but the weight is already smaller. Then for 2 2 for 2 I think I have missed this. Yeah, so 2 is connected with 5 with weight 4. 2 is connected with 5 with weight 4. Yeah, so we got this. After that, what we have? 6. So 6 is connected to this and this. This is not. So we have to consider this. So 6 parent is 6 itself, but the value already present is smaller. Then we got 7. So 7 is connected to 6. We will not consider this. 7 is connected to 8. We have to consider this. Then we have to consider this. So weights we have is 7 or 8. We have to fill it in 6, but the weight is already smaller, so we'll not consider this. Then we are done with 7. We have 8. So 8 is connected to 2, this and this. So 8 and 2 is already connected. 8 and 7 is not connected. What's the parent of 8? 2. We have to find 7, but we have to fill 7, but the value store is already smaller. Then for 7, what's the parent of 7? 7 parent is 6. The value present is already smaller. Then we have 8 and 6. 8 and 6. Parent of 8 is 2. We have already smaller value. Parent of 6 is 6. We have already smaller value. So some values is still infinity, minus 1 and infinity. But some values, some edges we contain. So if this is infinity, if the value is infinity or we have minus 1, we will just skip it. Then we got this. Then we got this. So we have to connect it. What's the parent of 1? Parent of 1 is 1 himself. No, we have this. So 0, 7 and 8. What's the parent of 0? 0 parent is 1. So we have this. What's the parent of 7? 7 parent is 6. We have to connect it with weight 8. So we are not literally connecting, we are just making a connection. So the connection made between these groups is via 8. So we have considered this, and we have to also decrement. Then we got 2 and 5. We got 2, we got 5. Parent of 2 is 2 himself, parent of 5 is 6. Then we have to make a connection with 4. With 4. So let's make a connection with 4. So then we have this. Then we have this. Then we are not done till yet. We have to iterate it further. This is infinity, this is infinity, this is infinity. Then we go to 5, 3. So what's the parent of 5? 6. What's the parent of 3? Now this is a single group. So parent of 3 is same as 6. So it is already in the same group. So we don't have to do anything. So let me show you the code for this also. So this, we have cheapest. We are iterating in the cheapest, and I am finding this array. Then we got u, v and w. This is my u, this is my v, this is my w. Source, vertex and weight. If the weight is maximum, means every node to current node is already joined. So this is the case. We don't have any edge. Every neighbor node to the current vertex is already considered or joined. Then we need to find the parent, like I have did here. Zero's parent, zero's parent we have 1. Then for 7 parent we have 6. Then if this is not in the same group, we need to do the union. We have to join this. We need to consider the weight. And we have to decrement our group. So 3 steps we have to follow. First we find our cheapest, then we join, then we reset. So these we have to done while our groups is greater than 1. So we have to do these 3 steps. So let me show you the code. So we have Boruvka algorithm. Inside this we have different groups, answer and maximum. Then we have union find. I hope you are already familiar with the DSU concept. Then we have cheapest. Inside this we are adding, for every cheapest we are adding 3 things: source, vertex and the weight. If different groups is greater than 1, we are doing 3 steps. We first need to find the cheapest point. So from every vertex, for every vertex we have edges. So we are getting the edges using our adjacency list. So its time complexity is v plus e. Then we have u, v or weight. Find the parent. If it is already the same group, just don't consider that edge. After that, consider the edge, but add the cheapest edge on the parent. Add the consider edge on the parent from u to v with weight. Then the next step, we need to add the edge. If we don't have any edge, just continue. Find the parent. In this term we have already joined nodes already. If this is already joined, parent is uh, parent a, parent b is equal, it is already in the same group, just continue. Else consider the edge, consider the weight, and as we have considered it, we have one less group. After that, just need to reset it. So just reset with -1 -1 to maximum, and we need to follow these steps if our group is greater than 1. So at the end just return your answer. So let's give it a try. I hope it will work. And let's talk about time and space complexity. Here we have log v. We are decrementing our groups outside. Then inside we have log v plus e. We are just accessing our agency list. And we have order of v. So we have just cheapest. Then we have again order of v. So we have solved this question. Code is provided in the description box. If you guys have any doubt related to this Boruvka algorithm, although it is not used often, so still if you guys have any doubt, feel free to ask in the comment section. Thank you all for watching.